Okay, so the plan for today is to finish up section 4.7 on optimization, work through section 4.8 Newton's method, and possibly start 4.9 antiderivatives. Maybe leave that till next time. We'll see where we are at the end of 4.8. The quotes of the day today are by philosopher David Hume. The first one, a wise man always apportions his belief to the evidence. Um, uh, this is one that I think speaks to uh, the stats course that I teach. I don't know why I had a brain fart there for a second, but uh, you know, the stats course that I teach, we talk quite a bit about updating beliefs based on evidence and so on, this like Bayesian interpretation of things. And yeah, a lot to think about there. But we ought to uh not take external information that comes in that kind of disagrees with our worldview. We ought not overweight it so that every little new piece of information that comes in, we're, flipping that way and back and all of that in light of new information. We want to, you know, obviously consider the fact that our worldview is um, pretty clearly based on a lot of past evidence, but we don't want to neglect new evidence that comes in. So, um, and there's also this important idea of Hume's guillotine, and we talk about things like this a little more in stats as well, sometimes called the is-ought problem. And what a lot of us are doing, a lot of our majors are related to subjects that tell us a lot about what we might call is statements. Um, so is statements, things like statements about how the natural world works, right? If we're studying physics or chemistry or engineering, maybe engineering includes a little bit more of the outside of things, but certainly when we're studying the hard sciences, we're saying this is how something works. We've found out some fact about the world. We have some knowledge. We can make predictions off of that. That's great. But then what ought we do, right? If we understand nuclear physics, ought we take that knowledge and make nuclear bombs, or ought we take it and make nuclear energy? Right? Those are different statements. So bridging the gap between is statements and ought statements, we have to, I think, recognize the lane that maybe we want to stay in as folks maybe more concerned with the is side of the world, and let the philosophers and folks handle kind of the ought side of the world, and being a little bit cautious that we don't think that because we've answered a difficult is question, that implies an answer to an ought question. In some sense, just because we're able to do something doesn't necessarily mean we should do that thing. Um, so that's the idea for today. Uh, I probably could have said that a little more cleanly and a little more clear, but uh, anyway, that is what it is. So we're continuing on with our discussion of MLEs, maximum likelihood estimators. Again, in part because the math is a little bit interesting here. We get to use this nice theorem where we can hit an objective function with a logarithm and make it a lot simpler to deal with. And also because this is an interesting application, right? This has to do with, in some sense, apportioning our belief to the evidence. In some sense, we have a model, say in this case, a normal distribution, or last time we saw the exponential distribution, and we want to fit that model to maybe some real world data that we've collected, and we're curious how to do that. So the normal distribution here, f of x equals 1 over sigma root 2 pi, e to the negative x minus mu squared over 2 sigma squared. Big, long, complicated formula, but it is what it is. Here, x can be any real number. And just a side note, maybe I should actually write this here. Pi is approximately 3.14. Just because we have lots of Greek letters floating around. Pi is the usual pi, 3.14, but our parameters mu and sigma. So just to be clear what the parameters are, the pi that we see in that root 2 pi is just a normalizing constant. It kind of makes a specific area equal to 1. and makes the whole area under the curve equal to 1, but that might be a little confusing as to how we can make the whole area under an infinitely wide curve equal to 1. That's something we talk a little more about in Calc 2. But so that's where the pi comes up. Kind of interestingly, pi pops out where we might not expect it. And but mu and sigma are the parameters. So mu is a location parameter, and sigma is what we might call a scale parameter or a shape parameter, something like that. And we use the normal distribution a ton in statistics and probability and stats. If you've taken Math 165 or a similar course before, you might have come across using standard normal tables and solving problems with normal distribution. If you haven't, again, that's not a prereq for this. Well, we said our objective function of interest is the so-called likelihood function, which is f of x1 times f of x2 and so on out to times f of xn. Let me write f of x a little bit differently here. So f of x is 1 over sigma root 2 pi times exp of that. So this way, it's just a little bit nicer that we don't have that up in the power. And I might even write this constant at the beginning instead of 1 over sigma root 2 pi. I might write it as sigma to the minus 1, 2 pi to the minus 1/2. And I didn't quite leave myself enough room there, but that is my probability density function that we're going to use to plug in our data to get our likelihood function. So this tells me that my likelihood function is, well, it's the product f of x1 times f of x2 and so on times f of xn. So if I multiply all of that together, I have, I guess, sigma to the negative n. I have 2 pi to the negative n over 2, just some constant. And then I would have like e to some power times e to another power times e to another power. That's just adding the powers together. Or that's e to the, well, I'd have negative something minus something else, and so on. The x's are changing. The two sigma squares are not. So I have a constant negative 1 over 2 sigma squared times x1 minus mu squared plus x2 minus mu squared, and so on out to xn minus mu squared. It's a pretty big, like nasty looking objective function, right? Now, this objective function is a function of two parameters, mu and sigma. We're going to basically take the perspective of holding one constant. So we'll assume that we've picked a number for mu, for instance, and then we'll find the value of sigma that maximizes the likelihood, and then vice versa. We'll hold sigma constant and choose a value for mu. So I think I will leave mu as an exercise. And as a hint, mu hat MLE, the optimal choice for mu under this this perspective, is the mean, or just the average. So the letter mu tends to represent the mean in probability theory and stats, and that is indeed what it represents here. That's why the parameter, this location parameter, was chosen to be mu. It represents the mean, and our best guess for mu would be we take our data that we observed and we compute the average, and that's what our guess for mu would be. That would be our best guess. So that's the answer. If you wanted an exercise, you could go through a similar calculation to what we're going to do for sigma, do it for mu, and show that this is what you get. Okay, so we would like to find the best sigma to use. And you might guess, if you've seen a bit of stats before, you might think, oh, this we're going to use, say, sample standard deviation. There's a little bit of a hitch here. That's almost correct, but we get a little bit of an interesting result. So that's also the reason I wanted to do this. We get an interesting result from this that we might not expect depending on how much stats we've seen in the past. Okay, so I'm thinking of my objective function, my likelihood function as being a function of sigma. I'm holding mu constant. Again, pi is just a number, and x1 through xn, those are data values that we got from the real world. Those are just numbers. So given x1 through xn and mu, I want to choose the value of sigma that maximizes this likelihood function, that in a sense creates a model where the data I actually observed is maximally likely to observe. I certainly wouldn't want to think that a model models a situation well if the data that I actually observed is, say, impossible under the model or extremely unlikely under that model. We talked a little more about the philosophy behind this last time. And again, the philosophy isn't super important. That's more for a probability of stats course or an engineering stats course, something like that. But we're using it as a setup for an interesting example, I think. Now, one thing I do notice is this likelihood function as a function of sigma is kind of annoying to work with. I have a sigma bit here and in the power of the exponential function. At the very least, I have a product of two functions of sigma. I mean, if I go, you know, if I go differentiating right away, I have to do at least a product rule. I'm going to have a bunch of chain rules. I don't know if I want to do that right away. But again, I can get this into a little bit of a nicer form by taking the log of the likelihood function. I can compute the log likelihood function, the natural logarithm of L of sigma. And remember that the value of sigma that maximizes L, because log of stuff is an increasing function, that value of sigma will also maximize the log likelihood function. Now, the maximum value, the output, will be different between the two, but we're only interested in the value of the input that creates a maximum. We're interested in the maximizer. So this is a perfectly fine approach. Part of the magic of the log is that the log of the product is the sum of the logs. And because we're, for these likelihood functions, we're multiplying a bunch of stuff together, differentiation of sums works a lot nicer. So that's where a lot of the magic comes in. So I have the first factor here, sigma to the minus n, plus log of the second factor, plus log of the third factor. But wait, log of e to the stuff is just stuff, right? So this is a plus all of this stuff. Well, that's really a minus. One over two sigma squared times these brackets. Now, something that we note about these brackets, what's inside of the square brackets? Well, x1 minus mu squared and x2 minus mu squared and all of that, these xi's and mu are taken to be constant, right? Mu is constant. This is just some big constant. Let's just call it k. I don't feel like writing it, 5 times, so we're just going to call that constant k and bring it down. And if we need to at the end, we'll substitute back in what it actually is. But for now, we'll just call it k. And this 1 over 2 sigma squared, maybe I will massage that a little bit. I'll call this a 1/2 sigma to the minus 2. And I'm almost there. I've got one more thing I want to do. And I'm being a little lazy here because I don't want to rewrite all of this stuff. Log of sigma to the negative n becomes negative n times log sigma. The log allows the power to come down. the log splits the product into sums, and the log gets rid of the exponential. Those are all super nice things that it helped with here. And that's one of the reasons that it's so common to deal with the log likelihood function instead of the likelihood function itself when we're maximizing, because it's just this process of multiplying things together. Logging it allows us to differentiate much more easily. Okay, so now if I take d by d sigma of the log of the likelihood function, log of L of sigma, all right, well, my first bit here, log of sigma differentiates to 1 over sigma. This stuff, I mean, it's complicated looking, but it's just a constant. It differentiates to 0. And then here I have a minus 1/2 sigma to the -2. I differentiate and bring down the -2, giving me a plus 2 over 2 is just plus 1 sigma to the -3. I have to subtract 1 off the powers to make sure I go the right direction, times k. That k just comes along for the ride. And I want to set that equal to 0. Right, to optimize, roughly speaking, I differentiate, set equal to 0, and solve. So I have negative n over sigma plus k over sigma cubed equals 0. And what can I do here? Maybe if I multiply by sigma cubed, so that gives me negative n sigma squared plus k equals 0, or I have that sigma squared equals k over n. Or in other words, sigma hat MLE, again, I use the hat in statistics to say that this is something that I'm estimating based on data. And then little subscript MLE is just to note that I'm using the maximum likelihood estimate, equals the square root of what's 1 over n. And then k was all of this stuff up here. And that's our answer. I mean, it's a little bit messy, but if you've had some access to stats before, you might actually recognize this. This is a standard deviation. This is a measure of variation. Interestingly, though, my maximum likelihood estimate is an estimate that's based on a standard deviation based on real world empirical data. For a reason that I don't want to get into here, we would expect to see n minus 1 in the denominator instead of n in the denominator. The n minus 1 would make what we call an unbiased estimate of the standard deviation, of the population standard deviation based off of the data, but we actually don't see that here. We actually just see that it's divided by n. So that's a very interesting result from a stats point of view. We would expect to see this same thing, but with an n minus 1 in the bottom. That would be our sample standard deviation. That would kind of make all of our different worlds align and everything mesh together nicely, but we don't see that here. We have a decision to make. Should we go with the unbiased estimator, which is not the one that leads to the maximum likelihood, or should we go with the MLE estimate, which is slightly biased? What are the trade-offs there? So this doesn't tell us, this calculation here doesn't tell us which one is best, but it tells us that the two are different. We get two slightly different answers depending on how we look at the problem, and we have a decision to make with trade-offs. So would we rather go this direction or that direction? If we have a large sample size, if we take a huge sample, it doesn't really matter, because if n is 1,000, the difference between 1,000 and 999 is quite small. But if we have a small sample size, 8 or 10 or something like that, this, this could be a decision that's not of, minimal consequence. So anyway, again, some of the stats stuff that I added in around the edges, is more just for general interest, or if you've seen some of this before, you might find it a little more interesting. If you don't understand the stat stuff, that's not a big deal. If you want to understand it better, you can, look up a YouTube video on maximum likelihood estimates or something, and that might explain it a little more, although it'll be a little bit hard to interpret if you don't have a bit of stats background. But the main calculus bit here is this section here. We have an objective function. We want to find the maximizer of it. We choose to find the maximizer of the log of that function. It'll be the same maximizer, different maximum output, but same maximizer. And it's much easier to do the calculation in the logged scenario. Last time I think I had mentioned this, but I left this as an exercise minimizing time to rescue. So one place that we see optimization pop up a lot is when we have a trade-off to be made, we insert a parameter and then we optimize over that parameter. We saw that with, say, Snell's law, where we were looking at the path that has the minimum time between 2 points. That's the path that light would take whenever it's going through 2 different media. I also posted the Professor Kenneth Young's YouTube video on action. So this concept in physics called action. And I was right that Veritasium video was on action, although I still haven't had a chance to watch it yet. So I've been somewhat busy with schoolwork and stuff around the house and all that. So I need to get to that. But anyway, so if you want a little more explanation on that from somebody who's much more qualified to explain the physics than I am, take a look at Kenneth Young's video. I time-stamped in there when the relevant portion is, but honestly, the whole video is worth a watch. It's a really cool idea that really brings together so many different parts of the field of physics. So if you're interested in that, take a watch at some point. But that's the idea here. We could, if we're a lifeguard, just jump right in the water, swim to the person, minimize distance. That's one way to solve the problem. But we could say, well, I can run on the beach faster than I can swim. If I run a little bit towards the person and then swim, I got to take advantage of the fact that I can run on the beach pretty fast, and then I can swim a shorter distance. The overall distance is longer, but my average speed is maybe a little higher. Maybe that trade-off is worth it. At some extreme, it's no longer worth it because I had to run on the beach so much that I've now increased the distance a bunch, and I still have to swim. If I go from here to here, the decrease in the amount that I have to swim is negligible. So being able to run faster on the beach doesn't really benefit me that much. But over here, the decrease in that distance might be greater. And it turned out that so the feel of this problem is quite similar to the Snell's law problem, if you needed a hint. It turned out that the optimal L to choose, the length that we should run on the beach before we jump in the water, is given by this here, where x comma y is the position of the person in the water, 0, 0 is the lifeguard's position, VW is our speed in the water, speed swimming in the water, and VL is speed on land, speed running on the land. And we note that if VL is much larger than VW, this number is really big compared to the others. This term goes to 0, and L optimal is about X. So if we can run much, much faster than we swim, then we should run most of the way on the beach and then make a 90-degree left turn and then swim towards the person. So we're minimizing the amount of time in the water. But if our speed on land and water are closer to one another, we would pick an intermediate point to jump in the water. That's where that trade-off would be best. Any questions so far? Okay, and then our last example in optimization, maximizing utility. And we probably could do, three, four, five, something more examples that I have in my notes that I think are interesting ideas. There's one with like um, 0 point energy. There's one with numerically approximating derivatives. There are so many interesting applications of optimization that we could work through, but you know, we have to cut it somewhere for time. So optimization, a very important idea in Calc 1, one of probably the top three or four important ideas in differentiation um, and a lot of interesting applications as well. But the example we're going to look at here is an economics example, maximizing utility. So let's go quickly through some of these definitions. Mathematically speaking, a utility function is a function f of x such that f prime of x is positive and f double prime negative. That is, it is increasing and concave down. So it looks like this. Our utility function takes as input the amount of some economic good. So it might be like, pizzas or something like that. It gives as output the utility. The derivative is positive, means that I would rather have more pizzas than less pizzas. That makes sense. If I have 10 pizzas, I, have as much to eat as I want. If I have one slice of pizza, I might want more. The second derivative being negative says we have decreasing marginal utility. So in other words, if I have a whole pizza, like that's a lot better than having only one slice of pizza. If I have 10 slices of pizza, I'm like, okay, I have enough that I can eat dinner today and have pizza left for tomorrow, or I could share with a friend. If I have like three whole pizzas, I mean, okay, those next two pizzas maybe are nice. If I really have a craving for pizza, I can have more. Or if I have a bunch of friends come over, I could, yeah, I guess give them pizza. If I have 20 pizzas, well, now it's starting to just become a hassle almost, right? Um, so going from like zero pizza to one slice of pizza is a huge benefit for me. Going from one slice to two slices is pretty nice. Going from two slices to like a whole pizza is okay. Going from one pizza to 10 pizzas is, less of a benefit. Or another way of thinking about it a little more abstractly is with money, like, the homeless guy with $0 to his name, somebody gives him a five, like there's his, lunch and dinner for the day. That five means a lot to him. If Bill Gates is walking down the street and finds a $5 bill on the ground, it pretty much means nothing to him, right? It might not even be worth his time to bend down and pick it up. So that's the idea of a utility function. We want more of economic goods, so having more stuff is better, but each additional extra unit means less to us. Okay, so and the amount of, say, something like happiness or positive psychological effect that an amount of good has to us, we call that the utility. So that's whatever kind of positive human effect that, it's like amount of happiness or whatever, like how much benefit this brings an individual for having that amount of that economic good. Okay, I mentioned that. So an example, we might consider a utility function, say like f of t equals the natural log of t. That is a function that is increasing and concave down. Its first derivative, 1 over t, and this would be, of course, for t bigger than 0. So 1 over t for t bigger than 0 is positive, and f double prime, negative 1 over t squared, is less than 0. So the natural logarithm is a utility function. As kind of an aside, some people debate um, on whether this is a reasonable definition. Like, should we also require that f of 0 equals 0, in which case log t wouldn't satisfy that. So if you have like 0 of a good, should you have 0 utility from that good? Or should you have Should you be able to have negative amount of a good, like if you owe somebody money or if you owe somebody pizza? We're not getting that deep into things. Okay, so suppose that we're going to use the logarithmic utility function, f of t equals natural log of t. And then suppose that we have an amount of income I to allocate to two goods, x and y. So maybe we have two hobbies. We like to go out to the movies and we like to eat dinner with friends. And we have an amount of income I that's our like hobby money for this month. We have to decide how many movies we want to see and how many dinners we want to go to with friends. And we know that good X costs p dollars or p units per unit of that good. So going out to the movies costs whatever, $20 each time, and say going out to dinner costs q dollars or maybe $30 each time we go out to dinner. And our question is, what does this trade-off look like? So if I spend more money going to movies, I have to spend less money going to dinners and vice versa. Of course, if I just said, how many dinners and movies do you want to go to each month? You'd say a whole bunch, right? I want to go to 100 dinners and 100 movies. And I don't know, maybe by 100 dinners you'd be sick, but I want to go to a bunch of dinners and a bunch of movies. But the thing that makes this interesting is that we have a constraint. So we have a type of problem here that is a constrained optimization problem. We want to maximize this utility function, the utility that we get from good x looks like log x, and we're going to multiply that by a. A is going to have something to do with like how much we like movies relative to going out to dinner. And good y, log y, is going to be the utility for a movie, and b will be something like how much we like movies relative to dinner, something like that. And this is subject to the income constraint. Well, this is a little easier to see where this comes from. If we go to, say, X movies that cost P each and Y dinners that cost Q each, the total cost is PX plus QY. And that should be our income, or our amount of income that we've allocated to these two goods. So we have I dollars to spend on movies and dinners, and that's where PX plus QY equals I comes from, our income constraint. And subject to that constraint, we want to maximize this utility function a log x plus b log y. So if I just said maximize this utility function without constraint and unconstrained optimization, then I just pick a large number for x, a large number for y, and right. But the point is that if I choose a large number for x, because my income is constrained, I then have to choose a small number for y, and vice versa. And of course, there are even some x's and some y's that are not achievable under this income constraint. If I wanted to go to 200 movies, that would probably be more money than I'm allocating to movies and dinners. Okay, so I have a little bit of a problem here in that my objective function has two input variables, x and y. But this is single variable calculus. How does this work, right? I mean, if we were in Calc 3 and multivariable calculus, maybe we could see this working out, but I have two input variables, x and y, and I somehow need to get this down to a question in one input variable. But I kind of realized that this income constraint, well, if I know how much I spend on movies, I'm assuming that I'm going to just spend the rest on dinners. Because log x and log y, those are both increasing functions, I would always rather spend more money on something than less money, all else equal. So if I spent half my money on movies, I wouldn't go and spend a quarter of my money on dinners. I'd spend the other half on dinners because spending more on dinners will make me more happy. It'll get me more utility. So my income constraint, I can solve for one of the variables in terms of the other. So for instance, maybe I have that x equals I minus qy over p. If I know how many dinners I'm going to go out to with friends, y, then I can just plug y into here and that'll tell me how many movies I should go to see x. We won't worry about the details of can you go to a half a movie or can you go to a quarter of a dinner or something. We're not going to really worry about that. So I can solve for x in terms of y, plug that into my objective function. So I have a natural log of x. So that's natural log of I minus qy over p plus b natural log of y. That's my utility function now. And I realize that I've eliminated the parameter or the variable x. And now I have my utility function phrased in terms of a single variable y. I was able to use my constraint equation, solve it for one variable in terms of the other, substitute in, get my utility function as a function of a single variable. Now I can do what I did before. U prime of y is going to be, well, okay, let's look at this. We have a times log of stuff. Let's actually come over here. Okay, so if I differentiate log of stuff, then I get 1 over stuff, or that is going to be p over I minus qy times the derivative with respect to y of, and I'll write this as I over p minus q over py. So derivative of log stuff is 1 over stuff, or that's p over I minus qy, times the derivative of I minus qy all over p. But if I break it apart this way, I can see that d by dy of I over p, that's a constant, that's 0. And then minus q over p times y, that differentiates to just negative q over p. That gets multiplied on from the chain rule. And then I have plus b over y. I see I get a little bit of cancellation. My p's here go away. I could have done some algebraic simplification up here and made this a log of I minus qy minus a log p, and that would have differentiated the 0 as well if I wanted to do that simplification. Either way, these p's go away. So what do I have? I have negative aq over I minus qy plus b over y. That's my derivative. And I want to set this equal to 0. Or this tells me that b over y equals aq over I minus qy. Cross multiplying, I have bi minus bqy equals aqy. Or what do I have? I have that bi equals a plus b qy. Or I see that I have b over a plus b times I. And if I'm thinking of this like a mathematician, I would solve and I would make it a times 1 over q equals y. But if I'm thinking of this kind of like an economist, I would probably leave it like this. And here y we're thinking of as the optimal y. Why would I leave it like this? Well, what is q times y? each unit of good Y costs Q. This is really the dollars spent on good Y. And what is on the left side, B over A plus B, that's a proportion of our income. So the dollar spent on good Y should be the proportion B over A plus B of our income. This would pretty clearly imply that we should spend the rest on good X. So in other words, PX optimal should be A over A plus B I. The amount of money we spend on good X should be the remaining proportion of income, A over A plus B I. And if we wanted to do that formally, we could say, okay, I found Y optimal here, but where was my all the way up here? I don't know if this is really going to copy nicely. Okay, that wasn't bad. Looks like that copied well. Oh, except for my divided by bar. So kind of economics and understanding the problem gives me the green bubble. But if I want to do this formally, do it completely mathematically, I see that QY is B over A plus BI. And then X is going to be I minus, well, I minus QI is I minus B over A plus BI over P, or in other words, PX equals, well, I can factor out an I and I get 1 minus B over A plus B, or that's A plus B minus B over A plus B. That's A over A plus BI equals PX. Either way, I get the answer. So I want to spend PX dollars on good X and QY dollars on good Y. And the proportion is going to be B over A plus B, proportion of my income I spend on good Y, and A over A plus B, proportion of my income I spend on good X. So I have this really nice proportionality, and I see that that's what the A and B up here really mean economically. So there are two ways that I can view A and B. If I have goods X and Y, and I know their prices per unit of good, I could ask a person, okay, like how happy would you be if you got this many steak dinners um and this many movies, right? Or what about this number of dinners and that number of movies? And I could then fit in my model, I could choose A and B to fit the choices that that person says. They say, for this value of X and Y, I have this much utility, and for that value of X and Y, I have that much utility, and I could use that, set up a linear system, solve for A and B. These parameters A and B tune the model to the individual, and then we can see how they ought to make their decisions, at least under this model, of course. But what do A and B mean, really? Well, what they mean is the proportion of that person's income that they would want to allocate toward good X versus good Y. Right. So if the cost of Y were to say double, then the person would want half as many units of Y. If the cost of movies doubled, I forget which one was dinners and which one was movies at this point, but if the cost of movies doubles, then I want to go to half as many movies, so I can still spend the same proportion of my income on dinners. I still want that proportion of my income to split that way. That's what the model claims. Now, if I observe people's behavior and I see that they don't make decisions that way, that might be a shortcoming of this model. Maybe I would choose a model that had parameters kind of like this A and B, but that didn't have that implication, right? So again, why do we care about things like optimizing? Whenever like you can look at a problem like this and say, well, if I actually had numbers for X, Y, VW, and VL, I could plug this into a calculator, try some different L's, or just have it solve it for me. Well, sure, but I wouldn't understand the model, right? I get more of an understanding out of here by solving the model abstractly and seeing, for instance, like what do A and B in some like moral sense tell us? What are they really representing? In some sense, they're just representing parameters that we use to fit this model to a particular scenario. But in another sense, they really tell us the inferences and the implications that the model is making, and we can decide whether those are implications that we think are consistent with reality and observed behavior or are inconsistent, and maybe we would want to choose a different model. Any questions on this one? So again, I tried to give some insight into um, some of the different problems from different areas that that use optimization, and some of the reasons why going through this uh, abstractly, going through this using calculus is actually beneficial, rather than just, if I just gave you a function and said find the minimum or maximum of this function on this domain. Well, you could pretty easily just plot it in your calculator and say where's the maximum, and it'd give it to you. But I don't think you'd be able to get this level of understanding really in any way using a calculator. Oh, and I suppose we really ought to check that U double prime is negative. Um, I'll leave that as an exercise. So U double prime is less than 0, so the utility function will be concave down. Um, we showed that F is concave down, but I think it's pretty clear that U should be concave down as well. Here, I should note that A and B are positive constants. That is actually fairly important. Right, we would always like to spend some money on some positive amount of money on movies and dinners. It's not like I would pay money to be able to not go to a dinner or something like that. So A and B are positive, P and Q are positive. And under that constraint, we can show that U double prime is negative. I think that's probably pretty clear from up above, but if you don't see why that's true, then take another derivative and argue that U double prime is negative. And therefore, we, of course, have found a maximum. We really wouldn't want to find a minimum utility and be choosing the worst possible choice. It's also, I think, qualitatively clear that we found a maximum because we found we found a single critical number. Everything is nice and differentiable. And pretty clearly, if we just spent 0 money on both of them, we would have like the worst utility. I guess we can't quite spend 0 money here because then we'd have 0 of good X and 0 of good Y. But if we spent a really small amount of money, we'd have a really large negative utility, and that would clearly be suboptimal. Okay, any questions on optimization? All right, moving on to 4/8 then, Newton's method. So Newton's method, we're kind of completely switching gears here. Newton's method is a method for solving a nonlinear equation. We want to solve f of x equals 0. If we have something like f of x equals g of x, just subtract everything onto one side and you have function equals 0. We typically think of this as being some complicated nonlinear equation that we can't reasonably solve by hand. So that is, we want to find a value that we call x star, such that f of x star equals 0. We want to find a solution of this equation. Okay, so one little side note, we had an equation solver that we've already run into. We called it the bisection method. And it used the idea of the intermediate value property or intermediate value theorem. that if I have an interval, and if my function is, say, positive on the right endpoint and negative on the left endpoint, and it's continuous in between, there's got to be a solution in the middle. So then what I could do is I could pick a test point, say, in the middle, and evaluate the function there. If the function evaluates to exactly 0 there, hey, I found a solution, I'm happy. If it doesn't, let's say maybe the function evaluates the positive here, there might be a solution on this right half of the interval, but I don't know that for sure. But I do know that there definitely is one on the left half. I can then ignore the right half and continue my search. Right, I would say pick a midpoint again. Maybe here the function evaluates to negative. So I would focus on this interval, and I would keep doing this, right? The idea is that I have a process that I have an initial, say, guess, or an initial constraint, something like that. And I have a process that when I run through the process one time, my guess gets a little better. I run through it again, my guess gets a little better, right? The interval over which the solution might exist keeps getting smaller and smaller. So if my guess is something just like the midpoint of the most recent interval, my guess should get closer and closer to the answer. That's the idea of an iterative method, is I have an initial guess, maybe it's an interval or a number or whatever it may be, and I have a process, and I run that process one time, my guess gets a little better. Another time, my guess gets a little better still. And I can leverage the fact that we have computers that can run a process a bunch of times. And I could run this bisection method 10 or 20 or 50 times on the computer and narrow down to an answer that is very, very accurate. And that's the general philosophy behind Newton's method as well. So the general philosophy, I'm going to jump down a little bit, skipping ahead a little bit, is suppose that we have an initial guess x naught, x subscript 0, our initial guess, our 0th guess. And we're also going to assume that it's near x star, near the answer. So it's not way off in left field. It's, kind of close to the solution. And then, oops, I forgot a subscript here. Then we can run a process. We can evaluate this right-hand side that has something to do with the function and the value of the derivative at that initial guess to get an update. And then I could take that update and treat that as my initial guess, apply the same process, and get another update. And I can keep getting updates, and each update, I mean, if everything goes well, should be better than the previous guess. Okay, so where does this update come from? Or really, what's the underlying idea behind Newton's method? What's the method? Well, near our solution, f of x should be approximately L of x, the linear approximation. So let's say I have some nonlinear function. Oh, that's a little too steep. Let's say I have some little linear function f of x. I have a solution here, x star. Now, if I can find x star, if it's a linear equation or something, I can solve it. I just find x star. So we're assuming that f is a function that is hard to find the solution for. E to the x plus sine x minus x squared equals 0. Well, good luck finding a solution to that algebraically. I have some guess, say x naught. It's not too far away from x star. Well, if I look at x naught and I consider the linear approximation, which I've drawn not so great here, if I consider the linear approximation, L of x, well, near x naught, the linear approximation is a good approximation to the function. That was one of our big results near the end of chapter 3, 3.10, which still irks me. that a math book has a 3.10 that comes after 3.9, but whatever. Um, so near x naught, the linear approximation looks more like f of x. But the linear approximation is a linear function. It's easy to solve for its root. So if I solve L of x equals 0, that should be kind of like solving the problem, solve f of x equals 0. Or in other words, I can find L of x equals, or I can find the solution to L of x equals 0 easily. That's just the solution to a linear equation. We'll call that x1. I see that x1 is closer to x star than x naught. It's not right on top of x star because solving L of x equals 0 isn't exactly the same problem as solving f of x equals 0. But because the problem that I've replaced solve f of x equals 0 with, namely solve L of x equals 0, those problems are close to one another. Finding the exact solution to an approximate problem should give me an approximate solution to the exact problem, right? There's this little kind of an interesting idea here. So if we can't find an exact solution to the exact problem, we kind of have two paths we can take. We can find an approximate solution to the exact problem. So if you've ever taken a physics course and you know how like um, a mass spring system is like a simple harmonic oscillator, it goes up and down like sine of x more or less. And you have a pendulum that swings and it kind of follows the same mechanics as a mass spring system. It goes back and forth like sine x, but not really for the pendulum because there's a Newton's second law for torques and all of that that's involved that it actually doesn't work so nicely. Yeah, but we kind of say, well, we have this system that leads to a certain differential equation. That equation is really hard to solve, but that equation is approximately like a much simpler differential equation, like the mass spring equation. And as long as our angle of the pendulum isn't too big, maybe 10, 15 degrees, something like that for a pendulum, we can replace one model with another. We can find uh, instead, so one way is to find an approximate solution of the exact problem, or we could alternatively opt to find an exact solution, the mass spring solution, which is an exact solution to that model, to an approximate problem. So there are kind of two different ways to attack such a problem. When we can't find an exact solution to the exact problem, we can find an approximate solution to the exact problem. That's maybe something like what bisection method does in some sense. Or we can find an exact solution to an approximate problem, which is kind of what we're doing here. I replace f of x by L of x, its linear approximation. I can find an exact solution to L of x equals 0. And hopefully that'll be close to the exact solution to the exact problem, x star. Okay, but what is L of x? Well, that's f of x naught plus f prime of x naught times x minus x naught. That's just our linear approximation formula. Now, what I want to know is I want to solve L of x equals 0, and I want that to be, call it x1. So I want L of x1. I want to know when is that 0? Or that's f of x naught plus f prime of x naught times x1 minus x naught, set that equal to 0. And solve for x1 in terms of x naught. Well, what do? I subtract f over, I divide by f prime, and I add x naught over. Yeah, missed the sign there. So that's what x1 is in terms of x naught. If I have an initial guess x naught, I plug it in there. I plug it into f. I'm assuming I can evaluate f fairly easily, but I can't solve f equals 0 very easily. I'm also assuming I can differentiate f and evaluate it. So that is an assumption for Newton's method. And there are some problems with Newton's method, particularly with convergence. Bisection method always converges if we can get it started, and Newton's method not so much. And some of the problems come from the derivative being in the bottom here. But I'm also kind of assuming that I can differentiate and evaluate. So that's where my update comes from, replacing f by its linear approximation around the guess, solving linear approximation equals 0 to get my updated guess. So what does the algorithm look like? Given an initial guess x naught that is, quote, near x, we iteratively compute, we keep doing this process, right? We plug x naught in, we get x1. Then we go ahead and plug x1 in over here to get x2. And then x2, plug x2 in and get x3 and so on. We iterate over that. We get xn plus 1 equals xn minus f of xn over f prime of xn. Note that if we ever hit on the solution, if we ever get, say x sub 17 equals x star, then f of x sub 17 is 0 by definition of x star. My update is 0. I guess as long as my derivative is not 0 there, right? And then x18 is just x17 and x19 is just x. So if we do land on a solution, we never go away from the solution. So, that's a nice little property that we might notice. So we iteratively compute a better update and a better one yet and a better one again. When do we stop? We can't just tell our computer to keep doing this because it'll keep doing it forever. We stop when either this criterion is met, that we have a small output and a small update. I want to make sure, or I want to find f of x equals 0. So I want to make sure that one of my stopping criteria is when f of x in absolute value, this should be in absolute values, is small, when it's f of x, xn should be close to 0 for me to succeed. And also my update should be small. Well, why is that? Well, imagine that I had a function kind of like this one up here, but maybe it kind of sits here really close to 0 on the output side for a long time. Whoops. And then crosses, right? Well, I could be all the way over here. Here's x star for this problem. I could be all the way over here and have a small in magnitude output. F of whatever this is close to 0, but I could still be a long way away from the input that yields a solution. But I noticed that if I have a situation like this, my derivative is going to be quite close to 0, and my next update will be quite large. So my update going from one guess to the next improved guess, if we're still making large updates, we probably don't want to stop. When my updates are small and when my output is small, that's a good stopping criterion. So this is the first stopping criterion. When f is small in magnitude and we have small updates, or unfortunately, like the bisection method will always converge. It'll just keep cutting the interval in half, and then we'd have a stopping criterion that's like when the interval width is below a certain number, make your last guess the midpoint of that interval, and then, and then be done, and it'll always terminate. But we'll actually see that Newton's method, and sometimes it doesn't terminate. It could be attempting to solve a problem with no solution, and it'll just keep trying to solve it and, run forever. Uh, or in other cases, it just, fails for other reasons. So for Newton's method, we always want to have kind of a safety in here so that our program doesn't just, keep running forever, doesn't just run into an infinite loop. So we set some maximum number of iterations, maybe something like, 20 or something, or 50, depending on how much we think each iteration is going to cost or how much time it's going to take. So we say if it doesn't converge within 10 iterations or 20 iterations, then break out of the program, return an error, say, hey, Newton didn't converge. But if it does seem to converge to a solution, this is what that would mean. Okay, so let's take a look at Newton's method. We want to find the solution of e to the x equals 4 minus x squared. It's 2 decimal places of accuracy. And we'll use the initial guess, x naught equals -1. All right, so the first thing that I notice is that Newton tries to solve f of x equals 0, so I've got to get all of my stuff onto one side. So I have e to the x plus x squared minus 4 equals 0. And now I can call this f of x. So I have f of x is e to the x plus x squared minus 4. And then I need f prime of x as well. I know that I need that derivative's on the bottom there. So f prime of x is e to the x plus 2x. Let me bring up my calculator and switch my share over. We don't use our calculator too much in Calc 1, but we will use it here. Okay, so let's keep this kind of organized. So I have I, my iteration. I have xi. So for iteration 0, x naught is -1. And then I have an update. So I see that I take my previous guess, xn, and then update it by subtracting off f of xn over f prime of xn. I'm going to call this update maybe like delta, say delta n. Or this is supposed to be I. Call it delta sub I. Keep my letters all correct. Negative f of xi over f prime of xi. And then I have x sub I plus 1 is x sub I plus delta sub I. Just adding these two previous columns together. And then xi plus 1 in the I equals 0 row, that's x1, that wraps over, or whoops, wraps over to here. And then we use that for the next line. Okay, so for I equals 0, delta 0 is f of x naught over f prime of x naught, or that is e to the -1 plus -1 squared minus 4 over f prime of x naught, e to the -1 plus 2 times -1. Whoops, and with a minus in front. So negative all of that. Or let's put that negative up top. So I have a 1 minus 4 is a -3. So I have 3 minus e to the negative 1 over e to the negative 1 minus 2. So there is 3 minus e to the negative 1 divided by e to the negative 1. Make sure to use the negative, the white negative button down here for negative instead of a minus. So e to the negative 1 minus 2. So that gives me about negative 1.61. And then my updated guess is going to be, since I already took care of the minus in my delta in my update, it's going to be my previous guess plus the update. So it's going to be negative 2.61. Or in other words, when I equals 1, xi is negative 2.61. Now, one thing I can actually do is I can do this a little more efficiently in my calculator. I did some of this simplification by hand, but I can see that it's going to be pretty tedious to do this by hand every time. So for a general I, delta I is going to be negative f of xi over f prime of xi, or it's going to be what? I'm going to leave the negative in front. And I'll have e to the xi plus xi squared minus 4 divided by e to the xi plus 2xi. Or in other words, my xi plus 1 will look like, so if I start with a negative 1, let me put that in here. My xi plus 1 is going to look like my previous answer. I'll do second negative to fill in answer. So this is referring back to negative 1 plus delta I, or minus. And then I have e to the power previous answer. So e to the second answer. And then plus the previous answer, second answer, squared minus 4. That is the numerator of my update, e to the answer, plus answer squared minus 4. That looks good. Divide that all by, open parentheses, e to the answer. So e to my previous answer in the calculator, my one line above, plus 2 times my previous answer. And now fingers crossed, that should give us negative 2.61. And there we go. So I could do this line by line like this. But benefit of doing this, it took me a while to write that in. But when I hit enter in the calculator again, it's going to perform that same calculation. Except that now the ANS, the previous answer, is the negative 2.61 that it'll plug in and give me negative 2.05. Now I can infer from this difference what the update was. Well, the update must have been something like 0.56. Right? It's the difference between these two. Remember, I'm looking to get a small update. So I can hit enter again. I get negative 1.97. And again, I can infer the update here. Well, that what had to be added on to negative 2.05 to get negative 1.97. That was about 0.08. If I hit enter again, I have negative 1.965. If I hit enter again, I see that I didn't change in that second decimal place. Now I wanted 2 decimal places of accuracy, and it seems like I have it. My update has not changed in the second decimal place between guesses 4 and 5. Really shouldn't call them guesses, between iterates 4 and 5. So I'm pretty confident with negative 1.96, negative 1.97, something like that. I might also want to check f at negative 1.965. So if I go second enter, I can just double check that this gives me a pretty small output. And remember, f is the numerator of this delta I. That's f of xi. So I can get rid of the first bit and the denominator. And I end up with just this e to the answer plus answer squared minus 4. That is just f. And since my answer was x5, my most recent answer, I see I get 10 to the negative 12th as an output, and I'm probably happy with that. Right? Typically, if I get an answer 10 to the negative 5th or 10 to the negative 7, something like that, that's quite accurate. 10 to the negative 12th is getting pretty darn close to the precision of the calculator or computational device for normal devices. Normal devices have, the calculator, Excel, whatever it may be, has maybe 15 digits of precision. So that's how we go about this. I could do this full tabular approach. And in fact, we'll do an example like that in Excel so we can see the whole table worked out. Or I can leverage my calculator's kind of refer to previous answer function to get a lot of these iterates quickly. I see that the difference between successive iterates gives me my update, and I can see the update is certainly getting small. It's less than 1 part in 1,000 at this point. And I see my output for x5 is also quite small in absolute value, something like 10 to the minus 12. I'm probably happy with that. I feel like I've converged to the answer, and that the answer is approximately negative 1.965. Now I want to jump ahead a little bit here. So I don't forget to. Let me actually just copy this down below. Okay. I want to jump ahead a little bit here. I've kind of mentioned a couple of things, and there are some important things I haven't mentioned. So let's look at a bit of an overview of Newton's method. What are the benefits of using Newton's method? Well, when it converges extremely fast. There's a rule of thumb that basically if Newton's is going to converge, it'll converge in 6 steps. That's a rule of thumb. It's a heuristic. It's not guaranteed to work or anything like that, but it typically does work. The really nice thing about Newton is that it exhibits quadratic convergence. In other words, the error on the next step kind of looks like the error on the previous step squared. Now, this quadratic convergence property kind of takes hold, so to speak, when we're quite close to a solution. So if you're 5 units away from a solution, the next guess isn't going to have an error of size 25. We're saying, if you're 0.1 away from a solution, your next error will look like 0.01, and your next error will look like 0.0001. Another way to say this is you double the decimal places of accuracy each iteration. Basically, once you have 1 decimal place of accuracy, the next iteration will get you to 2, then 4, then 8, then 16, and you're already at the limits of kind of standard computational devices without, doing special programming or something to get below 10 to the negative 15. So that's kind of where the like rule of thumb convergence in 6 steps comes from, is if you got 1 decimal place of accuracy from one iteration, then 2, 4, 8, 16 is like 5 steps. So if it takes you 1 or 2 steps to get 1 decimal place of accuracy, you're probably going to converge to an error that you're happy with within 6-ish steps. So if we were going to create a stopping criterion for Newton to fail, for our program to kick out and say, hey, I tried running Newton's method. I don't want to enter an infinite loop and crash the computer. Kick out and say, hey, Newton failed, try something else. I might want to set n max. Maybe it's something like 10 or 15. I could set it at 6 or 7. That might be a little aggressive. If I pick a bad x naught, it might take it a little while to get close to x star. But if I set it to 10, 15, 20, that should give Newton plenty of time to try to converge. And if it doesn't converge, something else has probably gone wrong. The other nice benefit of Newton is that it generalizes nicely to higher dimensions. This idea of a derivative generalizes to higher dimensions, and we can imagine having a function of several variables, function with several inputs, and we could look for what combination of inputs yields a zero output for that function. We could do basically Newton's method, just using a different perspective on derivatives. Some downsides of Newton's method. So when Newton works, it works very nicely. But Newton's a lot more complex than bisection. As an aside, let me jump back up here and make one more comment on that. Bisection method, we get 1 decimal place of accuracy. Well, that's like basically a factor of 10. One run of bisection method cuts our error by half, another run by a half, and another run by a half. So 3 iterations of bisection method gets me something like 1 decimal place of accuracy, right? I've cut my error by 1/8. Say that's pretty close to 1/10. So 3 iterations of bisection gets me 1 decimal place of accuracy. Maybe something like 7 iterations would get me 2 decimal places of accuracy, right? So if I wanted, with Newton, we said, 4, 5, 6 steps is going to get you like 15 decimal places of accuracy. If I wanted 15 decimal places of accuracy, I'd have to do like 45 or 50 bisection method iterations, or just like 5 or so Newton steps. So bisection method, if you can get it started, it's just going to it's like the turtle. You're just going to keep plodding forward and eventually get you what accuracy you need. But number one, you got to get it started. So you got to find that like minus the plus, for instance. And number two, it's a little slow relative to Newton. It takes more iterations. Now, as an aside to the aside, all right, I'm getting a little tangential here, but as an aside to the aside, you might ask yourself, well, if I run Newton or if I run bisection, even on a very nasty, something that looks a lot worse than this for my f, my objective function, if I actually program it into my laptop using Python or something, doesn't matter what, by the time that my finger is done hitting the enter key, Newton and bisection are both going to have an answer for me to 15 decimal places. 50 runs of bisection method costs nothing on a computer. And so does Newton's, right? And that's a good point. To do it once doesn't cost anything. Where we often see these used, though, is I have some big differential equations model I want to solve. I want to evolve the system in time for 10,000 time steps. And on each time step, I have, 5 nonlinear equations that need to be solved. So each time step, each little tick that I want to move the system forward in my computer, I've got to do 5 nonlinear equation solves. And I want to do that 10,000 times. Well, now all of a sudden, if I've got 50,000 nonlinear equation solves to do, and I mean, if Newton's method takes, 1 millisecond and bisection takes 3 milliseconds to do, well, if your answer takes 1 day to get back, versus 3 days to get back, you might actually care about that, right? So a lot of times these nonlinear equation solvers are embedded in much bigger problems as part of the solution method for that. So that's why we care about things like convergence. I mean, back in the day, in 1950, they cared because like the computer might not be able to do it, just Newton versus bisection. But today we care because the size of problems that we need to solve is much bigger. And if we have to do a nonlinear equation solve or several of them on every step, it is very nice to use a fast solver. Okay, there are some downsides of Newton though. Number one, it might not converge, but it'll continue trying. So imagine x squared plus 3 equals 0. We're looking for a root of this equation. With x1 equals 0, we're actually just going to flip-flop back and forth. Here's 1. We're going to get shot over here to -1, get shot over here to +1. It's just going to keep going back and forth. Keep going this way, and then that way. It's going to go -1 +1, -1 +1. Right? So there's clearly no solution to this. But Newton will try to find a solution. You told it to find a solution, it's going to do what it does, follow the tangent line down, use that as the next guess, go up, follow the next tangent line down. It's going to keep doing that. Even if we look at this and we'd say, that's silly, why would it do that? Well, you told it to do that. So it might not converge, but it'll continue trying. And that's one of the reasons that we have to have a failure criterion here. If it gets in a loop like this, we don't want it to run and crash the computer. We want it to kick out, 20 or 30 iterations later and say, hey, I couldn't find a solution. We might have a solution like x squared equals 0. But the problem with x squared equals 0 is that the derivative at the solution is 0. You might say, well, why do I care about that? That doesn't matter. Well, let me copy this over. Well, our update has a derivative in the bottom. So we actually, usually will still converge to the solution, even if the derivative is 0 at the solution, but we lose quadratic convergence there. So if this thing is heading towards 0, as this thing is heading towards 0, our update is kind of going to like a 0 over 0 kind of deal. And we lose quadratic convergence. We get back to something. I don't know why that font ended up funny, but we get back to something that's more like the binomial method or the bisection method type of convergence, a linear convergence, but with a more complicated process that has a higher cost for each iteration. We have 2 function evaluations per iteration instead of 1. So we'll still approach the solution. Newton will still find the solution here, but it'll do it much, much more slowly than if the derivative at the solution was not 0. And third is that it can easily approach the wrong root. If we have a function that has more than one root, we pick an initial guess over here, it's going to zero in on this root. But if I pick an initial guess like here, it might get shot all the way over here to the next one and start zeroing in on this root. In fact, there are really, really pretty diagrams that are basically running Newton's method on problems in the complex plane. And I have a few of them saved somewhere in a PowerPoint presentation. Maybe I'll try to pull it up for next time. But it's basically the equivalent of going through this real line and saying, if I pick this is the initial guess, which of these 4 roots does it converge to, and color it a different color? Root number 1 is red or something, so this point gets colored red, and this gets red, and that's red, that's red. But once we get over to here, now we get shot over here, so this region might be blue, and If I get a little further over here, I might get shot to this. So it's kind of this, like, you can think of a real line being colored according to which route you end up converging to for a given initial guess. But if you do it in the complex plane, it makes a two-dimensional colorful picture, and it's actually really cool. And it's also actually really hard to tell which route it's going to converge to um, based on your initial guess. You could have initial guesses that are pretty close to one route and that are pretty close to one another that converge to, maybe some of them converge to that route and that you expected, and some converge to a route that's really far away. Or if you have like a cyclic function, say sine x or something like that, you could imagine a situation like this where you keep getting like shunted further and further down the line and converge to a route that's way far away. So it can converge to a route that is not close to the initial guess, that wasn't the one that you wanted to converge to. And then lastly, we have to compute the derivative. So we have to compute the derivative maybe algebraically. Oops, how did that happen? We have to compute it. Trying to just select that. There we go. Maybe algebraically and evaluate it. Maybe the derivative is messy to compute or to evaluate. Or maybe we try to compute the derivative numerically, and it's just kind of a pain to do. We try to approximate the value of the derivative, but this function just isn't really cooperative, and approximating the value of the derivative is difficult. There is a solution to that, and that's to use the secant method, which basically does the same thing as Newton, except that up here, instead of taking a tangent line, it takes a secant line, and that helps to avoid some of the problems related to the derivative. But the secant method doesn't it loses some of the other nice properties of Newton's, like the quadratic convergence. I'm pretty sure secant loses quadratic convergence. So there are some benefits of using Newton, but there are also some downsides. Any questions on any of this? Okay, when we come back, we will walk through these last two problems and then move on to antiderivatives. I don't want to start this problem because we only have 7 minutes left, and I think it's going to take us longer than that to get through this one. And then this last one, we'll use Excel to help us with that and kind of build out the table in Excel. That's just another approach to solve this problem. So if you want to brush up on your Excel skills for next time or have it ready to go, we'll use that for this estimating pi problem. All right, I will stop the recording.